Welcome to Learning to Engineer. How to find out the operating region of a transistor. Whether the transistor is operating in active, in saturation or in cut-off modes, we need to find out. This question is mostly asked in competitive exams. We will also be in a position to decide the operating region of a transistor when we are implementing that in circuits. Basically, we know that there are three modes of operation. I'm sure you would have watched this video, and so when you are given a circuit, how to find that out? We are going to look at that in this video. In addition to that, whenever we are applying KVL, we will have one common doubt, whether I am considering the current direction correct or not. I am going to answer this question as well in this video. Let's get started. First, we will just glance through the three modes of operation of a transistor. First one is the common base configuration. In the common base configuration, we will have the base to be common to the emitter as well as the collector. So whenever we are biasing, the voltage will be applied with respect to emitter base junction and collector base junction. Either one of these should be in forward bias and the other terminal should be in reverse bias, so that we could get the transistor in active region. In this graph, when VCB is negative, when VCB is not connected like this, instead when VCB is connected like this transistor will be in saturation and this region is also forward biased. So when both the input and output terminals are forward biased, the transistor will be in saturation region. When both are reverse biased, the transistor will be in cutoff region. This holds good for all the three configuration: common collector, common base and common emitter. Just that the common terminal will be different, but the output characteristics will be same. I mean the curve path will be same, but the current which is at the output and the current which is supplied in the input will vary. Okay, so this is the basic idea you need to have in mind about the three modes of operation. Let's solve one problem in this concept. Consider this circuit. What is the operating region of the BJT? You are supplying plus 10 volt as the emitter voltage. This is in common collector mode. Okay, the collector region is common to both the transistor's base as well as the emitter. We need to find out in which region this operates. So, like I said, when both the junctions are in forward biased, then it is in saturation region. When both of them are reverse biased, then it is in cutoff region. When the input terminal is forward biased and the output terminal is reverse biased, then it is in forward active region. Okay. So our first aim is to find out this voltage between the base and the collector. Okay. And then we have to find out the voltage between the emitter and the collector. VEC. This is in common collector mode, right? So once we find out both these voltages, we have to find out the directions of this so that we can determine whether it is in active region, in saturation region or in cutoff region. Okay, so for that we are going to apply Kirchhoff's current law to find out IB. After we find out IB, we can find out any voltage in a transistor. So whenever you are given a transistor circuit, first thing that we need to do is to find out the current IB. Okay, the base current. Whichever mode of transistor it may be in common base mode, in common collector mode or common emitter mode, the first thing that we need to do is to find out IB. Okay, we have to find IB. And why are we finding out IB? Because beta IB will be IC, the collector current, and beta plus 1 IB will be the emitter current. So we will get all these three currents once we find out IB. So from these three currents, we can find out any voltage that we want. Okay. So we know that this is the NPN transistor and the voltage between the P and N regions of any semiconductor is plus 0.7, not any semiconductor, of any device is plus 0.7 volt, because for silicon the depletion region width needs a voltage of 0.7 volt for the current to cross that junction. So between the P and the N of base and emitter region, this voltage is 0.7 volt. Okay, so first thing that we are going to do is we are going to apply Kirchhoff's law in this loop. Okay, applying KVL in the base, emitter to base. Let's be more specific. Okay, applying KVL in the emitter base loop. What we will get? 10 minus 1K into emitter current. Okay, minus 0.7 volt, because it has to cross that junction, which is 0.7 volt, minus 270 kilo ohm into base current is equal to 0. What is IE? IE is beta plus 1 IB. What is beta? Beta in this problem is 100. So it is 10 minus 10K, 10 minus 1K into 101 IB. Clear about this? Minus 0.7 minus 270K into IB is equal to 0. So this implies that 10 minus 0.7 is 9.3. 9.3 is equal to 270 plus 101 will be 371K times IB. So what is IB in this case? IB is equal to 9.3 divided by 371K, which is equal to 0.02506 milliampere. Okay, this is the value of IB. What is IC? IC will be 100 IB, which is equal to 2.5 milliampere. And what is IE? IE is equal to 100 plus 1, 101. 101 IB, which will be something close to 2.6 milliampere. Okay, so now we have found out all these three currents of this transistor. Let's find out the junction voltages. VBC will be VB minus VC, right? So what is VB? The current through the base multiplied by this resistor, 270 kilo ohm. 270 kilo ohm, the resistance, multiplied by the current through it, which is 0.025 milliampere, minus what is VC? 1 kilo ohm into the collector current, which is 2.5 milliampere. So this is equal to 6.76 minus 2.5, 4.26 volt. The base collector voltage is 4.26 volt, which means the base is at a higher potential than the collector terminal. Now let's find out VEC, the voltage between the emitter and the collector. Okay, the current direction is considered like this. Here it is going into and here it's going outside. For our convenience, I'll just draw this diagram here. The value of VE will be 1K into the current through the emitter. Okay, the current through the emitter is entering into the junction as 2.6 milliampere minus 1K into the collector current is 2.5 milliampere. So this will be 2.6 volt minus 2.5 volt. Okay, so this region is forward biased and this is reverse biased. Hence, this transistor operates in the forward active region. Okay, so whenever we are given a BJT circuit and we are asked to find out the mode of operation of this transistor, we have to find two things. First is IB. Next, both the junctions voltages, whatever be the mode of operation, we have to find out both the junctions voltages and determine the sign of operation. If both of them are positive, it is saturation mode. If both of them are negative, it is cutoff mode. If the input terminal is positive and the output terminal is negative, then this transistor is in active region. we will also answer another question. Whenever we are applying Kirchhoff's law to a circuit, consider this case. Okay, whenever you are applying Kirchhoff's voltage law through a loop, say you are considering the direction of the current to be like this. It is going into the resistor A, it is crossing this junction. Let us call this voltage to be V1 for now. Okay, and this current is entering at this collector terminal and it is leaving here. So this is the direction of our current. So whatever be the actual current direction, doesn't matter. For our consideration of this KVL equation, this current direction is the master. Okay, so it will be I1 into RA, which is the voltage across this resistor, minus V1 because this is positive here. Okay, so this is minus V1 and it is plus 1 kilo ohm into IE equal to 0 under this condition. If, say for example, our considered direction is wrong, the current doesn't go in the clockwise direction, actually the current goes in the anti-clockwise. If that was the case, what would happen? This equation, when we solve, the current will be negative. So that we can understand that the current direction is opposite. Okay, so whatever be the actual direction of the current, whatever be the actual voltage, that doesn't matter. If our considered direction is in line with the original direction of the current in the circuit, then our values of the current and voltages will be positive. Otherwise, they will be negative. That's all. Okay, so whenever you are applying Kirchhoff's voltage law into a loop, you need not think much. You can consider any direction for your convenience, and later on from the results of your equation, be the voltage or the current, whatever you are going to find out from that KVL equation, based on that we can find out whether the considered direction is in line with the original direction or not. Okay, so thanks for watching. If you have any doubt, do let me know in the comment section or give me a thumbs up. Thanks for watching. See you in my next video.